Bueno, vamos a empezar. Hoy tenemos el gran placer de
Sí,
aprovechar de la visita de Joris, que él trabaja en un centro de investigación, bueno, un instituto de investigación en Francia que se llama IRD, y también tiene representación aquí en Colombia. Hay algunos
sí,
investigadores conozco algunos que trabajan en café, ¿no?
sí,
También conocemos uno que
sí,
trabaja
sí.
en café. Y bueno, como lo dijo, está en Brasil unos años trabajando en un problema muy interesante de Machine Learning con Sustainability y ecología. Entonces, muchas gracias por venir y queremos hablar.
Sí, gracias por la invitación. Ahora voy a hablar en inglés. So, yes, I am Joris. I'm a researcher in the IRD, as Fabrice just said. And today I'm going to tell you a bit more about my research and my philosophy about machine learning. And we're more specifically going to discuss resource-efficient computer vision development for sustainable applications. So before we dive into the technical, I'm going to tell you a bit more about me. So I'm French, but I live in Brazil since the beginning of this year. And I try, through my research, to contribute even a small way to try to improve living conditions of vulnerable communities and protect the environment. So that's why I kind of shifted my research focus. I'm also father of two boys, and if you don't find me doing my research or taking care of them, I'll probably be running somewhere. So I'm a researcher since 2022, a permanent researcher at IRD, which is the French Research Institute for Sustainable Development. And we are a research institute that focuses on all kinds of applied research related to sustainable development, and more specifically to collaborations with countries from the global south, which is basically South America, Africa, and Southeast Asia. And so we have a particularity to have research centers and representation in many countries, as you can see here. And we have about 30% of expatriates in the researchers. So for example, I am currently in Brazil and in Natal, which is a city in northeast Brazil. And I'm a visiting researcher at the Universidad Federal do Rio Grande do Norte. And I also am a co-director of an international lab, which is called IDEAL, which is Artificial Intelligence Data Analytics and Earth Observation Applied to Sustainability Lab, where we basically bring together researchers from France and Brazil in artificial intelligence, data science, Earth observation, ecology, and conservation and indigenous science, where basically our goal is to develop AI and satellite processing approaches to measure how the environment is evolving in the northeast Brazil and how sustainable development of local communities can impact or be positive to these dynamics. So my research is, I'm a machine learning researcher, and I apply my machine learning research to sustainability applications. And I study a lot not specifically the classical machine learning where we get a data set and we try to do as good as we can on this data set, but I try to study the whole applications where involving all the collaborators, the clients, and how we can optimize the whole process and not only the small machine learning part. And I studied this with a lot of collaborations with biodiversity researchers, with remote sensing specialists, where we work a lot on remote sensing with the links with the concepts of One Health and planetary health, which is basically studying the relationship between human health, environmental, and animal health. And I also have another line of research, which I won't talk too much today, but about AI safety, where we study how to certify AI models and computer vision models in safety critical applications, such as landing a plane or stuff like that. So first of all, in this presentation, I'm going to talk mostly about some approaches that can help to develop machine learning applications containing machine learning and computer vision more efficiently and effectively by basically integrating knowledge about the whole system and not only isolating the machine learning part. And so before we dive, I'm going to give a small background on how modern computer vision is being done so that we are all on the same page, and then we'll dive into more specific contributions. So computer vision is basically any kind of algorithms that aim to transform a numerical image, so a red, green, blue array, into some semantic information about the image. So for example, the classical example, we have two images and one model should say, this is a cat and this is a dog. So we have human level understanding about this big array of numbers that we want to extract. Some applications that we work on of computer vision is, this is an application of underwater image annotation where we try to estimate the proportion of the different kinds of coral species in an environment. So we work on that with my colleague Guilherme, who is a marine ecologist. And it's a classification computer vision algorithm. Another problem that we work on is remote sensing. So here's an example that we do in Brazil also about informal settlement mapping, which is basically a segmentation task where we need to give a class to each pixel. And the goal is to characterize, delineate and characterize favelas basically in Brazil, so we can link it to the health problems that they have in these communities. And the last one is, I wanted to illustrate the main families of algorithms, which were classification, segmentation, and here is detection, where we need to basically place a bounding box around the objects of interest. And we have some lines of work about runway detection for plane landing, and basically how we certify that so we can actually use it in real planes. So how we do this, now that we saw the applications, is traditionally we would do it with manual extractions of features. So we'd look at stuff, easy stuff, but hard to compute, but like colors, contours, and geometric key points. And from that, we would apply classical machine learning algorithms like random forest, and we would get some results. But what we noticed is that the higher semantic complexity, the higher level that we want to extract information, this basically don't work so well. So now what everybody does mostly is deep neural networks. So quick introduction, neural network is a bunch of neurons, artificial neurons. A neuron is linear transformation of a numerical input, where we then apply a nonlinear activation function. And then we can combine these neurons in layers. So we put them in parallel, and we have as many outputs as neurons that we put. And then we can combine layers, stack layers to get some more complex. And this is basically a universal approximator in the sense that there is a neural network that can approximate any function. So that's the most basic architecture. So once we do this, basically what we want to do for our task is to train this neural network to do the task that we want. So basically what we do is I'll explain the supervised training, which is the most classical. We get a bunch of images, we annotate them manually. So we want to give examples. So we'd say, this is a dog, and so construct what we call the data set, annotated. And basically we initialize at random, so we set the weights and biases at random in our model, run an image, get a prediction that's not good at the beginning, and compare this with the true label that we know. And then we compute an error, and we propagate this error back in the network to change a bit the weight so that the error becomes small in the next step. And we do this on a lot of images a lot of times, and we can train a neural network. Just a quick more information. So I presented you the feed-forward neural network, but in practice for images, it doesn't work, it doesn't scale, and has some properties that it doesn't get. So we use different kinds of architectures, but it's not very important for this talk. We use a lot of convolutional neural networks, and more recently, vision transformers. So with what we said so far, we can basically do a lot of stuff, and the process is, if you have a large annotated data set, and that's how big companies like Google do it today, they build huge data sets, they hire people to annotate them, then they have a lot of GPUs, computer power, they can train a neural network to do basically whatever you want if you manage to formulate the task and get the data. But in practice, in a lot of applications, we have limited annotated data and limited resources. So we need to find ways to still make use of all these techniques and this progress, but without all the resources. So we need to find smarter ways to do it. So what people have been doing is relying on what we call transfer learning, which is basically we would get these huge neural networks that are trained on a lot of images and that are often public. So we can take them and reuse them for other tasks, because processing an image is kind of, you have commonalities. If I want to classify corals and I have a model that has learned to classify a lot of classes, even without corals, it has learned to detect the contours, to join some basic shapes and make some concepts. So we can still use it. For example, even if my generic neural network haven't seen a bike, but it has seen cars, so it will know the concept of a wheel. And so maybe my generic neural network can extract some information like it has 2 wheels, it has a saddle, and it has a handlebar. And then what we do is, on top of that, we build a small neural network, which we call the head, neural network head, which will make use of this information to get the conclusions that we want. And for doing that, we need a lot less data now. So in practice, how we do this, we receive, if I collaborate with some clients or some partners that are not machine learning experts, they would give me a labeled data set. So that's my input. And I will know what task it is. So it's classification, so I know I need to maximize accuracy. And that's basically my input of my system. And then what I would do is split this data set into training and tests, because that's how we do it. And then I'll use the training set to train my whole architecture. This is something I need to fix. I need to find the right architecture for the head. This is fixed. And I'll spend some time working on the optimization and training algorithms so that I will spend time here and here to optimize that. So I think that's the next slide, yeah. Spend as much effort as you can here and here to maximize the test performance, basically. But if you look at the more complete view on how we develop a machine learning, an application containing machine learning, it's not so good to, so that all you saw in the previous slide is basically this box here. And considering that the data set is fixed, is not optimal, because the data set is for example, in my coral application, my colleague had to go on the field, take a boat, have a few divers, they would put this on the floor, take a picture, and do this in several places. And then they would spend a lot of time in the lab annotating the points. So that's part of the process. Then in my model training, I'll do it myself, or I will have a PhD student or a master's student spending a lot of time, 6 months, 1 year, trying to optimize the whole thing to get a good coral classification accuracy before I can send the model back to my colleague. So he can use it in production, which is also part of the process. So what he will do, he will collect more data on the field, use the trained model to substitute this part here, and then compute statistics on the images. So this species of coral was seen in this many pixels in my images. And then he will have some coral cover estimation. So that's what he's really interested in. He doesn't care about my accuracy. He wants to know for a specific area the coral cover is an estimate of how much coral is there. So basically, that's what I call the true application performance, the coral cover estimation here. If you look at the whole process, now we have a lot of labor here for data collection and annotation, a lot of labor from the computer scientists here in the model development and training, and a lot of resources also that we use. And we want to optimize what really matters, the true application performance, not necessarily only the model accuracy. So my vision is basically to try to find efficient strategies to optimize the whole process. So we want to minimize the labor here, minimize the labor and the computation here, and reach the desired outcome. Not get the performance as big and as good as possible, just reach something calibrated, like if it's this good, it's good enough, and we can run the application. So find efficient strategies to achieve the end application objectives while minimizing the other two aspects. And so today, I'm going basically to present two recent works that we developed. So that's what basically we apply in all our work with my PhD students, but so it's clear we'll focus on two main works. The first one is how we can calibrate resource allocations to maximize true application performance, and I'll show you the whole things that we developed for the Coral application with my colleagues. And the second one is about backbone selection as an efficient lever to improve performance without increasing development efforts. So first of all, aligning development efforts with application level objectives. So here is the application that we want to address. It's automatic benthic image annotation. So basically what my colleagues would do before we start working together, they would collect images, generate a set of random points in the image, and they want to get the class of each of these points. And they would do this for hundreds of images. And then they would annotate manually each point and spend, for 1 day in the field, they would spend 2 to 3 months with 3 students annotating the images. So they came to us and we started talking about, could we replace this manual work with some neural network that would do it automatically? But so there was a platform that they started using, developed in the US. And the main question that popped up was, okay, but when can we start trusting the model to delegate annotations? Because they would do some annotations manually, then the model would learn, then they verify the annotation, the model learns again, and they didn't trust it, so they would still annotate everything manually. So before answering this question, the next question was, what do you expect from the model? Do you expect the perfect model that makes no mistakes? In which case, probably you would never reach it. So you will have to keep annotating things manually endlessly. So they couldn't answer this basic question, which made us develop a next question is, let's see what's the impact of an annotation error on the final ecological metrics, which is coral cover for them. So basically, we started by modeling the whole application. So the whole application is we have a study area. I'll talk more about this map later, but it's just an area in Italy that we got the data from. And we want to compute the benthic cover proportions, so like the proportions of this green class over the whole area, so that we can know if we do this every year, we can know if it's increasing, it's decreasing, and make some policies about it. So to get this information of benthic cover proportion, benthic just means seafloor. We first sample quadrats. Quadrats is these squares that we saw earlier at random in the study area, like all the little squares here. And we get some images. And then these images, in each of these images, we sample the points, as I showed before. And we annotate the point either with the expert or with the computer vision algorithm to get benthic categories of each of the points. We compute some statistics and proportions, and we get the cover estimates for each of the classes. And what we see here is that there is actually multiple sources of potential errors. So before that, we would focus on make my model as precise as possible, make as little mistakes as possible, but that's not the only source of error that will lead you to something that doesn't work. So you can have insufficient sampling, so you have a few points to represent the whole area. You can have insufficient point sampling also in the image, and you can have annotation errors. So the objective is to basically, of this work, was to evaluate the joint effects of sampling design and annotation quality on the final cover estimates of the corals and the benthic cover. And we had some questions like, how do additional monitoring efforts, so they don't spend 1 day in the field, but they spend 2, would actually translate it to better monitoring cover estimates? How much accuracy is actually required to get something decent and reliable? And also, if we have more time and money to spend, should we spend it to get a better model or to collect more data? So to answer this question, we were lucky to find a very nice map from a colleague in Italy who collected a drone footage of this entire area in Tyrrhenian Sea, and then annotated with some algorithms points at centimeter scale. So we have the class for every centimeter in this, I think it's 500 square meters area in the region. So we could use it to basically start developing a simulator where we could try a lot of different stuff. So what we want to estimate is the benthic cover proportion over the entire study area. And so the good thing is now, thanks to this map, we have it. And so we can try sampling and making annotation errors and compare to the actual ground truth that we want to estimate. So we built this simulator, which is, you have a lot of options that you can try. You can place the quadrats in different fashions. So they like to do something like transect because it means moving the boat less times. So we give them this option. It's random or transect, and you can add more or less little squares. And we use that basically to compare. Then you can have different number of points in each of the images. And we also built an annotation error simulator where basically the user can fix the precision and recall of the model. So how much for each class. And then we start switching the true label to some different values to represent the precision and recall that the user has specified. So we can try different values and compare them. So in practice, we have all the parameters that we discussed so far. We put them through the simulator, and we get the final benthic cover proportion estimation, which we compare to the true proportion, and we get the error. But that's one iteration. So that means if I run the simulator 2 times with the same parameters, I get different answers because it's all stochastic. I think that's just what I said. So what we did is instead we did Monte Carlo simulation on that. So we ran the simulator 10,000 times for each configuration, so we can start having distributions of the error and compute some more advanced metrics on that and compare different scenarios this way. So we did a lot of experiments. Like the 3 first ones is about sampling strategies because my colleagues were really interested in that. So is it okay to do this transect that they were doing and this kind of things? I'm not going to talk about it today, but what we are going to discuss is about annotation error effects and also comparing resources allocation strategies. So we have identified the best quadrat placement and quantity scenarios from the previous questions. So now we have 50 random quadrats and 10 points per quadrat, which is enough. And what we started to do is try different configurations of recall and precision, changing between 50% to 100%. So we have very bad models to perfect models. And this is the mean absolute error. So that means in one iteration, on average, I have 1.40% coral cover error. And this is the bias. So on average, my difference with the true value. And what we can see is like, okay, this is lower than this, which means that if I have a model with 100% recall and only 50% precision, and I spend a lot of effort making it to the perfect model, then the precision of the whole pipeline of the monitoring, the coral cover estimation is decreasing. So all these efforts for having less precise estimations in the end. We'll discuss about why later. So that's for a class that has low abundance, for a category that has low abundance. So it's rare in the map. And now that's for a category that has high abundance. You can see something different. So now this region doesn't work anymore. But this is still lower than this. So that means the optimal configuration for the model is not the perfect model. So why is that? It's because if my class is rare, the previous one, so in my sampling is probably not seeing it as much as it should. So if my model makes error by over-predicting it, then it increases its appearance, so it makes it better. So I'm not saying we should aim for this performance, because we don't know it. Every class is going to be different map, but maybe that's not so worth it to spend 6 months, 1 year, 2 years getting the model from 70%, 70% to 100%, because it's really hard to do and the return is very poor. Now this, yeah, that's basically what I just told you. And now the second question that we wanted to answer is, if I have more resource to allocate, should I allocate it to get more samples or to improve my model? So annotate more data so that the model learns better. So we compare two scenarios, one where we collect 200 samples in the area, and we have a model that average 75%, 75%. And the other one, perfect annotation, so basically expert annotation, and we only collected 50 quadrats. So basically the time they spent annotated, they didn't spend it in the field. And what we can see is that the average error, so by having a model that's less precise, we introduce some bias. So basically the mean is not exactly the true mean, but the average error is actually decreasing. And what we claim is we don't really care about bias here, because in practice we have only one occurrence happening. So what we want is this occurrence to have as low error as we can. So basically a bad model is giving you some bias, but a low sampling gives you a high variance, which is actually dominating the process. So basically that's the main conclusion. What we concluded as machine learning experts, we should prioritize methods that perform well with few data and fast, instead of methods that perform well on the long run. So prioritize time to deployment over perfection, and focus on good enough accuracy to enable faster monitoring, so that they can really spend little time, have a model that works, and spend their time collecting data, which is their added value. But it's limitations from this study. We had only a single high-resolution map to do all this. The fact that it exists, it means we should consider this question before developing new applications, but we cannot take all the conclusions as absolute. So basically what we saw here before, we were saying spend as much effort as you can here and here to maximize test performance. And what we saw here is we don't really want to maximize test performance, because it doesn't really necessarily translate into better application. So I changed it here, and spend the right amount of efforts instead of spend as much effort as you can. If we can define what's sufficient, it's better for the development process, because else it's an endless pursuit. Like PhD student can spend 3 years doing a better model and still having 5 PhDs ahead to keep doing the work. And now what we are going to address is the here. So optimization and architecture is basically what we spend a lot of time doing, and what the whole community is mostly doing. And the pre-trained backbone that we use is actually, what I claim here is, people use backbones by default and don't spend as sufficient time on that, whereas it's a really easy lever to leverage to get better application performance at a cheap development cost. So that's what we are going to discuss now, optimal pre-trained backbone selection. And before we start, I'll give you a quick experiment so that we can start thinking about it. So that's a data set, an experiment on a data set called Oxford Flower 102 flowers. It's 1,000 images, so basically 10 images per flower species, and it's a classification problem. So if we develop a neural network for that, the easy way, we would basically take a feature extractor, so a deep neural network pre-trained. ResNet 50 is a very common one, and in all the tutorials you'll see some ResNet 50 at some point. And then you'll be the train set, a test set. You extract the features with your feature extractor, so you get the characteristics that I was talking about. And then you train an MLP head, so it's the neural network head, to classify the species. So that's the basic way. We did a small neural network, and then you compute the accuracy, and we saw that we got 75% accuracy on 100 classes, so it's not so bad. And so if we want to improve these results, what people would do usually is they'll try to have a better head, add more neurons, something like that, or they'll do data augmentation, rotate the flowers, change the illumination, or regularization. They add some stuff to the the loss function so that it gets better, or they change the learning hyperparameters, twist the learning rate, and you can spend a lot of time doing all these things. Really, 6 months internship can spend a lot of time doing all this just to get this to 80% and be happy. But what if we just change a string in the whole code? Like we change just this string here, and we put it to this model. K-former, I don't even know what this is, but it's a model that exists and that you can get freely online in the internet. And now I just change a string, so I spend 1 second, and I'm at 99%. So how do I know that's K-former? Because I did a lot of experiments, and I found that this was a good one, not the only good one, but so it's not so easy to do. It's not like I know it's this one that's going to be good for my data.
There is so many possibilities for this. Okay.
So the problem is, which one should I use? I know it's a good idea to change, but which one should I use? So for example, if you take the PyTorch library that's referencing all the models, last time I checked, it had over 1,500 pre-trained models. So they have different architectures, CNN, vision transformers, different sizes, different iterations of the same model, the different pre-training data sets. Some are pre-trained on ImageNet, some on bigger ones, some vision language models, a lot of stuff, different pre-training methods as well. So it's hard. So how do people choose in practice? The most common approach is what I told you, is just use the one you used to use, the popular one. So ResNet 50, VidBase, people use VidBase a lot. If you want some efficient net, mobile net, some people say, it's smaller, so it's good, it's more efficient. I'm using that. VGG, because historically it was good. And now, for example, last year, Facebook released Dino V2, and they did a lot of advertising about this model, so people are using it a lot. So no question, it's more what people are doing. It's Dino V2 works well, I'm going to use that. It's not a good solution. I just showed you ResNet, for example, in the previous example was not a good choice.
Cannot make you federate with all of that or part of them?
We'll talk about it. We can. It's more expensive, but yes, we can. Another option is do benchmark studies in the communities. So I'm showing one benchmark study that was released last year. It's pretty good. They compare different pre-trained backbones on different data sets, and they report all the results. So we could say, I'm going to use the best one from the experiments that these guys did, which is good. They provide us the best backbone overall, the best lightweight backbone, the best backbone by task and stuff like that. So, okay, good idea. But, so if you look at the 3 backbones that they say were the best, it's basically these 3 orange ones here. So here, what you see here is one data set. I think it's GTSRB's data set on road signs classification, and it's Eurosat accuracy. It's a data set on satellite images classification. It's 2 data sets that I selected at random, and I started to plot the performance of all 1,500 model of this library. Each point is one model. And what we can see is that if I choose the best one, I think the best one was this convNext, then it's definitely not optimal for my first data set, definitely not optimal for my second. And if I take even a ResNet 50 model, there is a lot of ResNet 50 available in the library, and depending on the one I choose, I can be here or I can be here. So it's really hard, because the best backbone, the problem is it's limited coverage. So they tested maybe 25, 50 backbones. It's very little. And it doesn't take care of the future, because if new models are released, they're studied. They overemphasize on average performance. The best on average is not necessarily the best for my case, and I don't care about the best on average. I want to build an application for a specific data set. And they neglect the implementation variability. They would say ResNet 50 is good, but which ResNet 50 are they talking about? So what we proposed is to have dynamic experimental selection of the best, because that's the only solution that we could find. And we formalized the problem that we call VIBES, Vision Backbone Efficient Selection, which the idea is basically for a specific task T and a specific data set that we have, We want to find the best backbone B in a huge backbone pool under a time budget constraint. So I don't want to test them all. I have 1 hour, and I want to find the best backbone in 1 hour. So I'm not going through all the formalization of mathematical formalization because of time. But so we formalized the problem, and from the formalization, we could define the entire solution space. So all the possibilities to make things faster than exhaustive search. And we also defined a way to compare approaches, which we call the backbone selection efficiency curves, which is simple. In the x-axis, you basically have the time you spent searching, and here you have the performance that you reached, and some of the variability because it's a stochastic process. And so you can compare curves and say, if a curve is above another one, it means that it's more efficient. And you can say maybe sometimes some methods are good in the short term and then bad in the long term. And we always put the fixed data set, which was the one from the benchmark study here, just to compare how long it takes to find something better than the best on average. So we did some experiments. So the solution space I was talking about is if you want to search faster than exhaustive search, you can either evaluate the models faster, so have some proxy evaluations that's faster to compute. So we basically replaced the full regression with learning free models, KNN, neurocentroid, or you can optimize the sampling. So because you take models at random and test them, instead of having purely random selection, you can try big model first or small model first, or you can change the data sets that the models were pre-trained because to increase the diversity that you're seeing. And so we did some experiments to compare that on 4 data sets in a low data protocol. So we wanted just 10 classes per class, 10 images per class. And we did the backbone pool that we used was 1,300 backbones. It was a heavy search. And yeah, the conclusion is, I'm not going to show everything here. I'm showing on a single data set, but the conclusions are on the average of the 4 data sets that we tried. It's basically that within 10 minutes, the basic vibe, so random search, which is the blue one here, in 10 minutes or maybe 12, it was already better than most of the generic backbones. And in 1 hour search, you were already much better than the generic suggestion backbone. So it means basically you should do it. Spending 1 hour to get better results is not so much, and 1 hour on a single GPU instead of having all the tests that we said earlier. And the other thing is the best way that we found was to do some dataset cycling, which means we should try a model that's pre-trained on ImageNet and then a model that's pre-trained on another dataset and cycle this so we have the max diversity possible. And now we come to the comment from Fabrice earlier. So if you don't want to spend time searching, we also found that models can be combined and you increase a lot the chances of success. So why is that? Some experiments that I did back then about face classification. What we can see is that the best model in these 3 models here is this one. So that's overall performance. But for a specific class, which was this guy, it appears that it didn't work so well, whereas the 2 other models worked well. So if you combine all them, you get the performance of the good model, and probably you can get some complementary performance of the other 2. So that's basically what we did. We developed an architecture to have multiple network in parallel and try to do it as good as possible. And what we saw is that it's much more robust, and it's even better than the best model, usually. So not so surprising, but the problem with that is that it's costly. So one thing we did with a master student this year was to try to do ensembles of lightweight backbones, so only small models, and we try to use the conclusions we had from the previous work to build the ensemble so that we maximize the pre-training dataset diversity. And we basically show that with only lightweight backbones, we can build an ensemble backbone that's not so expensive and that's more robust than the biggest ones. And finally, the last thing I'm going to talk about backbones here is one thing that we're investigating is navigating the generic specific pre-training spectrum, which is most of the backbones that I talked about were trained on generic data sets like ImageNet, which has cars, bus, dogs and cats, and thousands of generic classes. And the question is, could it be better instead of having 500 million images, generic images, if I want to classify corals, for example, to have another backbone that's pre-trained only on 10,000 images of underwater, but are specific to my task. So this would be a less usable backbone, but it can be used by all the community of coral images, for example. So we did this investigation for corals. So we basically took 3 models, one very generic one, the same architecture, the exact same model, but one pre-trained on the generic vision language data set, one pre-trained on specifically on biodiversity images in general, so more specialized, but it has also images of biodiversity, land biodiversity, and one smaller one pre-trained specifically on coral images. And so as you go down, you get more specificity, but less data, less quantity of data. Okay, I didn't put the results, but anyway, we found that specific is a bit better, but not so much. We were a bit disappointed. So now what we're investigating is, because usually the specific starts with this, and then you pre-train here, and then you pre-train here also. So it's an additional effort, and it has a lot less discounted cost in the long run because less people are going to use it. So we're trying to investigate if it's worth it to do this kind of models.
Marco, could you mute? Marco, ¿puedes mudar?
Marco?
Si Medina daba algún tipo de comentario adicional, sería muy bueno tener.
Silenciar. No, sin problemas. And we did this also for another application, which was the favela application that I talked earlier, where we investigated first if satellite-specific models, which is getting popular over the past few years, were better than generic models. So we found that, yes, it's much better. So models basically pre-train on satellite images of the whole planet, but not on cats and dogs images. And now what we're trying to investigate is if we can push if we can push this specialization further by doing, so the satellite models, they train on the whole planet. So basically they have a lot of forests, a lot of lands, and we are interested in urban classification, so we don't really care about that. So we're trying to define our own models that train only on cities. So can we have urban specialization? And we want to push this further even because we're interested in Brazil, have some regional specialization as well. So some model that see only South America and see if it gets better. So quick take-home message before we conclude. So improving machine learning specific metrics on a specific data set through architecture and optimization improvement is often an endless pursuit, as I was saying. You can spend ages trying to get these few additional percent. For example, gaining a few percent on ImageNet has occupied the whole community between 2012 and 2021, basically. And it was like thousands of researchers trying to get the best model on. It's interesting, it pushed the boundary further and it's good, but if your goal is to develop a specific application, you should, before spending all this time, make sure that you first have properly defined the performance that you need for your application. Because once you know when you reach success, then you can stop and do something else. And if your success is 100%, you're never going to reach it, probably. And the second thing is, try to properly map all the levers that you have to make your application better. sometimes the classical way is the hard way, and you have some very simple stuff like changing the backbone that you can do, and that's going to make your application better. So try to aim for low cost, high reward first. And then once you know you have the good backbone, you can spend time to make things better. And thank you for your attention. And if you have any questions, I'm happy to answer.
Thank you very much. Question? Ah, no, pero...
Habla despacio. Habla despacio.
Si tú hablas despacio en español, te voy a contestar en portuñol.
En portuñol.
Ok. Bueno, en Machine Learning obtener los modelos pues, con una currency de 100 es casi que imposible, ¿cierto? Pero entonces ahí hay un desfase, ¿cierto? Hasta qué tan óptimo el problema les permite a ustedes llegar, como dicen, no, en la currency nosotros necesitamos una currency de 95% para que ese error no nos afecte, digamos, esa clasificación, nosotros, todo ese trabajo que llevan pues, tú con tus colegas, o sea, cómo determinan ese margen de error que pueden tolerar.
So about when you stop, when you know what accuracy do you need, how do you know what accuracy do you need? And that's what I wanted to illustrate with the first problem that it's scenario specific. And my claim here is that developing this application where we could compare different, like the simulator, took me probably less time then I knew we don't need so good. So 70% is sufficient, but it was for my application. Maybe for other 95% is not sufficient. So you need to spend some time modeling your problem, talking with the person with who you're developing, to know the final task, to know how errors impact the final task. So it's not, there is not single answer, but I think it's an important process because then you know what you need and what you're trying to achieve. Yeah.
I had a small question about the possibility of using this kind of model in small devices. It's possible to have small devices and a lot small computational power.
So depends on the model, but there is a huge field about decreasing model size and building efficient models. There is some efficient models. Usually they are not the best one, but they are good enough. And there is two areas. Either you design a small model and you train it and then you release it, and you can find among the 1,500 models, you have maybe 200-300 of them are small models that can run on your computer, on your mobile phone or something like that. And the other area is people are trying to get big models and either remove all the unnecessary neurons in them so that they run faster, or transfer the information contained in the big model into a smaller one. So there is a huge field of research. It's called distillation usually. There is a lot of possibilities. Usually it's a trade-off. Smaller models is less good. It depends on what you want. We discussed that with, for example, my colleagues for corals, like, would you be interested in annotating in the field directly? Not so much. So, and we have one big GPU. They don't have time constraints. One medium GPU there. So you need to know also what you want to achieve. Like, one medium GPU is going to take some time to classify a lot of images, but you need to know, do you need your answer today, like in 5 minutes, or is it okay if I give you your answer in 2 weeks? For them, it was really okay. So we just get as much performance as we can, and that's because on this application, that's what we needed.
And so you mentioned that because it was the beginning of our conversation, that you are studying some disease.
Yes.
With these images, is the images you show about favela? Or?
No. So in favelas, the favela project, I have two big projects about satellite images processing. The favela one is something we do with Fiocruz, which is the biggest health and epidemiology organization in Brazil. And so basically, they came to us because they found out that during the COVID crisis, some favelas were very affected and a lot of people died, and some other favelas were not. So the idea was, how can we explain that somehow? So we started, first of all, we needed to delineate them. So we had this whole piece of work. And once we had a good model to delineate the favelas, it had learned some characteristics about the favelas. And we started to map this with measurable quantities, like the number of roads, the number of intersections between roads, which basically represented how chaotic was the organization. And we showed that the more complex the structural organization was, the more they were impacted by COVID and also by heat waves, because there were also health-related problems related to heat waves because they have a lot of them. So that's what we did for favelas. And we have also another big project, it's a European project called Mosaic, where we work at the French Guiana border and at the three border with Colombia also, in Leticia. And we studied the links between illegal logging, so people trying to find gold, and deforestation, and malaria. Because usually when these people go there and start cutting trees, we can see it from the sky, from the satellite, and it means more breeding zones for mosquitoes and humans presence. So it's kind of so we have all this line. It's not finished yet. It's an ongoing project, but we work a lot with local communities about that also, where they help us monitoring and annotating mosquitoes and stuff like that.
Here we have this problem. We need data in satellite imaging and try to get the environment characteristics and train it and train the model using this satellite imaging. It's a big problem. I don't know.
So similarly, like usually with satellites, you have a little data annotated because you need to go in the field, measure stuff, and it's hard. But these satellite-specific models, they're actually open and very good and can be reused. So I think it's a good starting point also. But we're starting to have the same problem because everybody is developing their own now, and we have a lot of models. I think every year it's 30, 50 new models, and so
the model choice is becoming a real.
So my student who is working on he always makes jokes with me. Who's working on developing the urban specific models, and it's called remote sensing foundation models, and he's always telling me, I feel like there is more people building foundation models than people using them, which is kind of true. It's like a popular thing to do.
So the curve of the number of models in time is exponential.
For now, it's exponential. I think at some point it will become.
Okay.
Hopefully,
we are still in the increasing part.
For the satellite one at least, because
yes, okay.
Satellite models were, I think the first one was 2021. So in 2021, people started thinking, it might work. And the thing with satellites is there is a lot of satellites also. So it's really easy to have a new idea. People used satellite Sentinel, which is the European, and Landsat. I'm going to combine this with another satellite and then add more data. And so it's really easy to make any combinations of the available satellites and build a new model. Yeah.
Okay, more question? Or in remote, is there any question in remote? So thank you very much for a very nice talk.
Thank you.